Let's talk about computer chips, the tiny brains inside everything from your phone to your coffee machine. These chips are the unsung heroes of our digital age, quietly powering the devices that shape our lives, from the simplest gadgets to the most advanced supercomputers. Every swipe, click, and tap you make relies on billions of microscopic transistors packed onto a sliver of silicon. The race to make these chips smaller and faster is one of the fiercest on Earth. It's a relentless competition with companies and countries pouring billions into research, all to squeeze more power into less space. The stakes? Faster phones, smarter AI, and the backbone of tomorrow's technology. At the heart of this race is a machine so advanced, it borders on science fiction, the EUV lithography machine. It's a technological marvel, the result of decades of innovation, and it's so complex that only a handful of people on the planet truly understand how it works. It uses extreme ultraviolet light, so short in wavelength it's absorbed by air, to etch impossibly small circuits onto silicon wafers. This light is so powerful and precise, it can carve features just a few nanometers wide, enabling chips to be faster and more energy efficient than ever before. To create this light, a laser blasts molten tin droplets, vaporizing them into plasma hotter than the sun, 50,000 times a second, all inside a vacuum chamber. The process is so extreme, it's like creating a tiny star in a box, just to print the next generation of microchips. This is the only way to make the world's most advanced chips. Without EUV, manufacturers simply can't keep up with the demands of modern electronics, from AI to cloud computing to self-driving cars. Without EUV, you're stuck making yesterday's tech in a world racing ahead. The difference is like comparing a horse-drawn carriage to a rocket ship. One is stuck in the past, the other is shaping the future. Access to EUV isn't just about faster gadgets, it's about national power and who controls the future. The ability to produce cutting-edge chips determines who leads in everything from economic growth to military strength. The countries and companies with this tech set the pace for AI, military, telecom, and more. Whoever controls EUV technology shapes the digital landscape, influencing everything from global security to the next wave of innovation. For years, the keys to this kingdom have been held by just one company. Their machines are so rare and valuable, they're guarded like crown jewels, and every delivery is a geopolitical event. If you want to lead in technology, you need these chips, or you're locked out of the next era. The future belongs to those who can master this microscopic world. And now, a new player is about to shake up this high-stakes game, promising to change the balance of power in the world of technology forever. So, who actually makes these miracle machines? The ones that power our phones, computers, and even the world's most advanced AI? The answer might surprise you. It's just one company, ASML, a Dutch firm that stands alone at the very top of the chip-making world, holding a total monopoly over the most advanced chip-making equipment on Earth. If you want an EUV machine, the only tool capable of etching the tiniest, most powerful chips, you have no choice but to go to ASML. There are no alternatives, no competitors, and no substitutes. Each of these machines is a technological marvel, costing over $200 million, weighing a staggering 180 tons, and requiring a global logistical ballet just to deliver it safely to a customer. Why does ASML have this monopoly? Because building one of these machines is almost unimaginably difficult. Even the world's best engineers have tried and failed. ASML spent decades and billions of dollars developing EUV technology, relying on a global web of 4,500 specialized suppliers, each contributing a vital piece to the puzzle. Take the mirrors, for example. Crafted by Carl Zeiss in Germany, they are so flawless that if they were stretched from Europe to Asia, the tallest bump would be less than a millimeter high. Their perfection is almost beyond comprehension. Every single component is a masterpiece of engineering, sourced from the world's most advanced companies, and assembled with almost surgical precision. This entire ecosystem is ASML's fortress. Reverse engineering a single machine isn't enough. You'd need to replicate the entire global network of expertise, suppliers, and technology. For any rival, it's like trying to recreate a thriving rainforest by planting a single tree. The complexity is staggering and the odds are nearly impossible. ASML's dominance makes it not just a business, but a strategic asset for the Netherlands and its allies. Governments treat it like a crown jewel, with security and oversight to match. Who gets access to these machines is a matter of global power. The United States has made absolutely sure that China, its biggest tech rival, is locked out of this technology. And that's why ASML now finds itself at the very center of a global technology tug-of-war, with the future of innovation hanging in the balance. China has long been the world's factory, but it's always relied on others for the most advanced chips. This dependency is a strategic weakness. China spends more on chips than oil. Determined to change this, China launched a national drive for semiconductor self-sufficiency, led from the very top. Billions were poured in, mobilizing top scientists, universities, and companies like Huawei. The mission: build a domestic chip industry from scratch, including the Holy Grail, EUV lithography. When the US blocked China from buying ASML's machines, the message was clear: you can't buy your way to the top. So China set out to build its own, no matter the cost. How do you catch up in a race you're decades behind in? You recruit the people who've already run it. China quietly targeted former ASML engineers, especially those with deep expertise in EUV. Lured by big incentives, these experts brought invaluable know-how. Not just blueprints, but the hard-won lessons of what works and what doesn't. One key recruit, Lin Nan, former head of light source tech at ASML. This wasn't just about stealing IP, it was about acquiring the human capital to shortcut years of trial and error. These engineers knew the pitfalls to avoid and the tricks to make things work. For ASML, it's a nightmare. You can't stop knowledge from walking out the door. By leveraging this talent, China dramatically accelerated its timeline. The king's own courtiers were now building a rival castle. China's strategy was a mix of imitation and bold innovation. They reverse-engineered older ASML DUV machines, dissecting every part to learn the basics. But ASML's design is so refined, China's early prototypes had to go bigger and bulkier to work. Instead of just copying, China's researchers at CIOMP developed a new light source, SSMB, which could be more efficient than ASML's method. This dual-track approach, copy what works, innovate where you can, gave China a shot at leapfrogging patents and maybe even surpassing ASML. The result, a clunky prototype, but with the seeds of a disruptive new technology. China isn't just catching up, they're trying to chart their own path. It's a risky bet, but it could change the game. Why the sudden urgency? US-led sanctions. The US, fearing China's tech rise, imposed strict export controls to block access to advanced chip-making tools. The goal: slow China down and keep the West ahead. But the sanctions backfired. They turned chip self-sufficiency from a long-term goal into a national emergency. China had no choice but to go all in, pouring resources into its own EUV project. The restrictions, meant to contain China, instead fueled its determination and innovation. The US tried to build a wall and gave China every reason to break through it. In 2025, China announced a working EUV prototype, a stunning achievement that shocked the industry. But a prototype isn't a production tool. ASML's first prototype took 16 years to become factory-ready. China hopes to do it in less than half that time. The challenges are immense. The machine must run 24/7, with near-perfect reliability and precision. Even tiny errors can ruin entire batches of chips. Achieving high yields is a brutal, years-long process. China's prototype proves the science works, but now comes the hard part: industrialization. Turning a lab marvel into a reliable factory tool is a whole new mountain to climb. This phase will test China's engineering, quality control, and ability to scale. The first summit is reached, but the real race is just beginning. Victory is still far from certain. China's challenge isn't just building one machine, it's replicating the entire ecosystem behind it. ASML relies on thousands of specialized suppliers. China must now create domestic versions of everything, from flawless mirrors to precision lasers. Each component is a massive project on its own. Even with perfect parts, making the machine work reliably in a factory is another huge hurdle. Chip fabs are ultra-clean, controlled environments. Any flaw can ruin production. Integrating a new, unproven machine into this process is a daunting task. Meanwhile, ASML is already rolling out next-gen machines, moving the goalposts further. By the time China catches up, the frontier may have shifted again. The race is relentless, and the finish line keeps moving. What does China's EUV breakthrough mean for the future? It's a seismic shift, not just for the semiconductor industry, but for the entire global technology landscape. For decades, the world's most advanced chip-making tools have been tightly controlled by a handful of Western companies, with China largely on the outside looking in. Now that dynamic is changing. Even if mass production is still years away, the monopoly is broken. Sanctions failed to stop China's rise. The mere existence of a working prototype signals that the technological gap is closing, and the global supply chain is being reshaped in real time. ASML's dominance is safe for now, but the long-term picture is uncertain. The company's expertise and market share remain unmatched, but the pressure is mounting as new players enter the field. If China brings its EUV machines online by 2030, it could create a parallel tech ecosystem free from Western control. This would allow China to set its own standards, develop independent supply chains, and potentially export its technology to other nations. This could split the world into rival tech blocks, with incompatible standards and supply chains. The seamless integration we've come to expect from global technology may fracture, forcing countries and companies to pick sides. The era of a single, globalized tech standard may be ending. Instead, we could see the rise of two distinct technological spheres, each advancing at its own pace and in its own direction. Companies may have to choose sides in a new technological Cold War, weighing access to markets against the risk of being cut off from critical innovations. China's prototype is more than a machine, it's a symbol of shifting global power. It represents ambition, resilience, and the determination to compete at the highest level. The West's lead is no longer unassailable. The balance of power is tilting, and the world is watching closely to see who will set the pace for the next era of innovation. The race for tech supremacy is wide open. Every nation, every company, and every engineer is now a potential game changer in this high-stakes contest. The future just got a lot more unpredictable. The only certainty is that the next decade will be defined by rapid change, fierce competition, and unprecedented innovation. And, perhaps, a lot more intense.